Okay, so this is the reactions of alkenes part 1. And so if we look at the structure of an alkene here, we have a few things that we can sort of generalize in how they react. So how does this work? Well, remember that an alkene has a pi bond that's there in between it. We have one sigma bond and one pi bond. And so we can draw this like so. And so remember that the pi bond here is above and below the plane of the alkene. And so it's this pi bond here that's going to react. This is going to serve as our nucleophile. These are where the available electrons are in this case. So if we look at basically the basic mechanism or the general mechanism of how this is going to work, we can think of adding HX to this double bond. So we can treat this with some acid, for instance HCl, right? So HX here, this is kind of like adding an electrophile, so you can think of it also as E+, right? We're going to add this electrophile to this alkene. And what you'll notice is the center of electron density, which is our pi bond, is going to attack the electrophilic portion of this, which will be the hydrogen, or it would attack an electrophile likewise. And then we generate something where one side of the double bond gets the hydrogen and the other ends up with a positive charge. And so this is our carbocation. The next thing is the X minus here in this case can come in and add to where our carbocation is to form the final bond. So you can see now that we have our completed structure where we've added HX in this case across the double bond, but this is in general how the alkenes are going to react. You're going to end up with this carbocation intermediate, and then something's going to come in and attack our carbocation. So we just saw the addition of HX, or an acid, across a double bond, and that was the case when the double bond was symmetrical. But what happens when the double bond is unsymmetrical, right? What happens when we have an unequal distribution of carbons on either side of the double bond? For example, if we draw something like this, where we have a double bond that has two substituents on one side and no really substituents besides hydrogen on the other side. So where does the carbocation end up in this case? So if we draw our reaction again, this time we'll use HCl as our reactant here, or our reagent, and so we can draw the general mechanism, whereas we have the double bond attacking the hydrogen, which is of course our electrophile in this case because there's a dipole that exists between the hydrogen and the chlorine, right? So the hydrogen is very strongly electrophilic in this case. And now you can see that we have the possibility of forming two separate carbocations. We can form this one, or we can form this carbocation. So the question becomes, in this case, which carbocation is the more stable carbocation that is formed here? Well, it turns out that, of course, you're going to form the one that's more substituted, right? So the one that's more substituted here is this one, which is a tertiary carbocation. So this is the carbocation that is formed, and you can see this in your product distribution as you'll form very little of the other product that is resulting from the primary carbocation versus the product that is resulting from the tertiary carbocation. So if we just take our example here and finish it out to show the product, so here's our carbocation. And then of course now we have Cl- that could come back in, and the Cl- then very quickly attacks our carbocation to give us our final product. That looks like so. So what have we seen here? Well, what we have just seen is an example of Markovnikov's rule. So Markovnikov's rule states that in general that you're going to form the more stable carbocation during one of these electrophilic addition reactions. Right, so you're going to form the more stable carbocation, and an easy way to think of this is sort of by the moniker of the fact that the rich get richer, right? So you can think of it where there are more hydrogens, the H is going to go where there are more H's. So in the previous example, we formed the carbocation that was more substituted. That comes about by putting the hydrogen on the end where there are more hydrogens. And so this shows that we form the more stable carbocation. If we look at the previous example, it demonstrates this concept that we're going to form this more stable carbocation. So again, we can just kind of repeat that just to show you one more time. That if we treat this compound with an acid at this point, this guy over here has no hydrogens, and this guy over here has 2 hydrogens, so of course the hydrogen is going to go where there are 2 hydrogens. This is a perfect example of Markovnikov's rule, and this shows how the H adds where there are already more hydrogens. So if we treat this again with HCl, you can see here that we're going to form the carbocation on the side where there are less hydrogens, or you might think of it as more substituents. In other words, alkyl substituents is what we're talking about here. And so there you go. That allows you to form the more stable carbocation. And then we can just simply have our Cl- come in and attack that to give us the carbocation, or the product. So in general, we're looking at the more stable carbocation. Now, one of the reactions that alkenes undergo, besides the addition of HX, is as a reaction that we hydrate them. In other words, we're going to add H2O across the double bond. Right? So we can do this in one of 3 ways. And the first way, number 1, is using a strong acid. So we can do this with some heat and a strong acid. So the general sort of reaction structure of this is by treating some alkene here with water and a very strong acid, and then of course we usually need a little bit of heat to go with it. And so our general reaction structure or product looks like this, where we've added H and we're going to add this OH here across our double bond. So mechanistically, how is this happening? What does it look like? Well, of course we can take our alkene and then we're going to treat it with our acid catalyst that we're going to use here. And so this H+, which remember, this H+ is from our sulfuric acid that we're going to use here. And the first thing that's going to happen is our double bond is going to attack the electrophile, which in this case is H+, serving here as our Lewis acid, just like the alkene is serving as our Lewis base. And the hydrogen goes on one carbon and the other carbon ends up with a positive charge because we've taken a bond away. And now we have water that's surrounding it, and water can come in now and attack our carbocation. If water does this, then you can see that we have the resulting structure. Oh, that should be a methyl group there. And we end up with water now that is attached to our carbon here, and we have two more methyl groups that are on the side. And then at the end of the day, we used acid as a catalyst, so we're going to regenerate our acid catalyst. And so water is going to come up and pick up the excess proton that is here. And we're going to end up with our final product. Those should be methyl groups, by the way, not hydrogens. My apologies. Now, what we notice here is that this follows Markovnikov regiochemistry. And it turns out that one of the drawbacks for this is that it's not suitable for reagents or substrates that are acid sensitive, of course, because you're using a very strong acid. So is there a way we can do this without using such a strong acid? And it turns out that there is a way that we can do this, and the one method that we can do is oxymercuration. So this is method number 2 for hydration of an alkene. And if we look at the overall reaction structure or mechanism, then we see something that looks like this, and we're going to treat this with a reagent that starts with mercury acetate, in THF and water, and then we're going to use sodium borohydride as our next reagent here. So a little bit of definitions here. What does the acetate look like? Well, we'll get to that momentarily. Let's just draw the product here very quickly. You can see again, just like before, we've added our HOH to our compound, and here is what the acetate moiety looks like. So this is what is attached, where the negative charge would be is where it is attached to the mercury. And THF is a structure that looks like this. It is a 5-membered ring with an oxygen in the center there, and it's tetrahydrofuran is THF. And this is basically a solvent to help solvate all of our organic compounds. They're insoluble in water. And then of course sodium borohydride is a reagent that delivers a hydride, and it looks like this. Remember, boron wants 3 bonds, and so if it has 4, we have a minus charge here. And then of course we have our sodium. So let's look at the mechanism for this. So what's going to happen here is we have, of course, our mercury. And it's going to add to the double bond in such a way that the double bond is going to attack the mercury. And what this is going to do is this is going to kick out one of the acetate groups that are on the mercury here. And then the lone pair is going to come in and add again to the other carbon. So we don't actually form a real carbocation. We form this merconium ion here. That looks like this. And then the next thing that's going to happen here is water is going to attack. And it turns out that water is going to attack at this point, the more highly substituted carbon. If they're both the same, you end up having mixtures of places because it doesn't matter, right? So now we have our mercury that's still on here, and now we have water that has been added to our carbon, and of course this has a positive charge. And then we kicked off one of the acetate groups, and so one of these acetate groups now can come in and pick up the lone proton that's hanging on here, and put the electrons back onto the oxygen. And then you can see that we now have our OH. But we still have the mercury to deal with. And so the next reagent that is added, which is why this is, by the way, listed as number 2, we let this reaction happen first, and then subsequently we then add in the next reagent. And the next reagent then basically gets rid of the mercury and produces a hydrogen, replaces it with a hydrogen. So just some key points about this. This adds in Markovnikov fashion so that we get the more highly substituted alcohol. Now the third method of hydrating an alkene is hydroboration. And it's important to note that in this case we're going to use BH3, which is a very strong Lewis acid or borane. And this is going to give us anti-Markovnikov addition of an OH. So we have this highly reactive Lewis acid that we're going to use here, BH3. So now we can look at our overall reaction. And so in general, what we're going to do is we are going to add BH3 to this, but there's sort of a catch in this reaction, and that is that once we add our BH3, notice that there are 3 hydrogens on BH3, right? And so for every 1 molecule of BH3, we need 3 molecules of our alkene. And so we end up with something that looks like this, where we've now added this BH3 across the double bond. And so we end up using now for part number 2 of our reaction, so BH3THF would be step 1, you would write that with number 1, and then we would use our H2O2, hydrogen peroxide, sodium hydroxide, and water as number 2. Notice that we now get 3 OHs. Right, so it's a 1 to 3 reaction mixture here. And so it's important to note here that BH3 is going to react in such a way that all the hydrogens on BH3 are going to be replaced with an R group, right? So it adds once, and then it adds again to a separate alkene, and then finally adds one more time, right? So just keep that in mind. And again, this is going to be an anti-Markovnikov reaction. So we're going to put the OH on the least substituted carbon. So let's look at the mechanism and how this is going to work. And let's also explore why we get anti-Markovnikov addition. So we're going to get syn addition. In other words, the H and the OH are going to add to the same face of our double bond. They add at the same sort of face on either side. Remember, the double bond is planar, right? So they're both coming from the same side. So it's easier to look at with a ring. And so here you can see our alkene, and now we're going to have our BH3, and you can see that the way that this is going to work is it's sort of a cyclic addition here, and so these are going to have to add to the same face of the alkene. And now we're going to end up getting our first intermediate that looks like this. And then remember that this is going to happen now 2 more times to replace this, but for the for the point of brevity, I'm just going to write H2O2 here and OH minus just to go ahead and finish this up. So that's OH and K and water and hydrogen peroxide. And so here's our OH here, and you can see that it adds to the least hindered carbon in this case. And the reason that it's going to add to the least hindered carbon is because of steric congestion. And we can explore that in just a moment. So if you were to look at this again, and you can see the methyl group, you can see that the BH2 that's over here versus the H is smaller, right? So this sort of methyl group is going to kind of block it. So it's going to have to flip and add the way that we have it shown there above. So your BH2 is going to add where there is the least amount of steric hindrance. So what this does is this gives you the addition of an alcohol in non-Markovnikov regiochemistry. In other words, to the least substituted carbon. Your OH adds on the least substituted spot. And again, I just want to caution you, we just kind of abbreviated this slide. But remember that for one BH3, you're going to have 3 alcohols that are there. So whereas I have BH2 that's attached to this is going to happen 2 more times, right, with the same compound, just as I did in the previous slide. Now, another reaction is the addition of X2. Right, so what does that mean? Well, this is the addition of an halogen, and so this works with Br2, Cl2, or it can work with I2 as well. Fluorine, not so much. Right, so in general, we're going to have our general sort of reaction, and I'll just draw this here with X2 for the time being. We'll do an example with bromine, but remember that it works also with Cl2 and I2. And so one of the important aspects of this reaction is that we end up getting trans addition. So you can't really tell when it's a single bond that you end up with that's not locked in any configuration. But when you use a ring is when you can really see what happens here. So here we're going to use Br2, and if you draw Br2 out, it looks like this, and I'm just going to put lone pairs on one bromine, because that's all we need here for this reaction. And it turns out that the double bond is going to attack one of the bromines, which of course is going to make one of the other bromines kick out. But at the same time, these lone pairs are going to come back in and add at the other end of the carbon, or the double bond. So now this forms a species here on one face of the double bond called a bromonium ion. If it was a chlorine, it would be a chloronium ion. And now what you can see is that bromine in this case is now forced to attack from the opposite face. And so it's going to come in and add in our example, it's going to add above the other bromine. So we have the bromonium ion forming on the bottom face, and so now that this bromine adds, it's going to add from the top side of our bromonium ion. And so now we get two bromines that are added on to our ring, and they're going to be added in trans fashion. So you can see that they're opposite from each other, and this is due to the fact that, remember that our double bond is planar, and we add the first bromine on one face, so that face is completely blocked, and the only way for the other bromine to add is from the opposite face, and so this leads to our trans product, or our trans dibromo compound. Now that brings us to the next set of reactions, which is the reduction of alkenes. And so this is going to convert them into an alkane, and so we do this by the syn addition of hydrogen gas, or H2, to an alkene, and we typically use a transition metal catalyst, whereas the most popular one is in general going to be palladium on carbon. So it's basically just palladium that is on some charcoal, essentially, it looks like. And it's usually about 10% palladium on carbon is a typical amount that you use. So basically you just mix all of these together under some hydrogen gas and you get your hydrogenated product. So the general sort of reaction that we're going to have here and you typically are doing this here with hydrogen gas and our catalyst, and then we do it in usually some alcoholic solvent, so ethanol tends to work well. There can be many different mixtures or ratios of solvents that you use, and what you can see here is that the hydrogens are going to add from the same face of the double bond, so we get the syn addition again of our hydrogen. Right, so the hydrogen is going to add either to the top or bottom face of our alkene, but they both add at on the same face. So another example of this would be something that looks like this, where I have now a carbonyl moiety. This would be a ketone, and we have our double bond in there. And so we're going to do the same reaction, and What's important to note about this reaction is that what you can see in the product is that only the alkene here is going to get reduced. We're not going to reduce the carbonyl, so we're going to leave that alone. That actually takes much higher pressures if you want to do that, and usually it's not done. Likewise, we can do another example where we have an aromatic compound which looks like this. So this would be a benzene, and then we're going to attach some groups here to it, and you can see now that we have an alkene in the middle. And it turns out that the only thing, when we draw this reaction, the only thing in this case that is going to be reduced, we use palladium on carbon, is our alkene, not our aromatic compound, which is a conjugated alkene. So our aromatic compound stays intact. All right, that's it for part 1 of reactions of alkene.